This is Nathan. He's a first year student at SB and he's taking Infocom Security Management. He has no clue on what is pipelining and how does pipelining works. In this video, Nathan's friends, Daniel and Samuel, will be going through what is pipelining and how pipelining works. Today we're going to talk about what is pipelining. Pipelining is the process of accumulating and executing computer instructions and tasks from the processor via a logical pipeline. It allows storing, prioritizing, managing, and executing tasks and instructions in an orderly process. This is also known as pipelining processing.
So to understand how pipelining works, we first have to look at how a computer executes an instruction. Firstly, the program counter accesses the instruction memory and the instruction is retrieved from the instruction memory. The processor then decodes it to examine which type of instruction it is. Meanwhile, the registers may be read. What is in the register may be an instruction, a storage address or data is then fed to the ALU. The decoding logic tells the ALU the instruction to be performed, whether it is an add, subtract, or XOR. Finally, it will then write to the result to the register. Or, if it's a load and store instruction, we access the data memory and write it to a register. So what pipelining does is it breaks down a sequential process into subprocesses. Each subprocess is run as a dedicated segment that operates simultaneously with all other segments. So typically, in an unpipelined way, cycle 1, the instruction 1 is fetched. In cycle 2, instruction 1 is being decoded. In cycle 3, instruction 1 is moved to the ALU. In cycle 4, instruction 1 is moved to the memory. In cycle 5, instruction 1 is then written. So, as you can see, it moves in a sequential manner. The latency for instruction 1 is 20 nanoseconds and the throughput is also 20 nanoseconds. As you can see, this is not a very efficient way of running an instruction if there are many instructions to be run. So now I shall explain to you how an instruction is executed in a pipeline manner. In cycle 1, instruction 1 is fetched. In cycle 2, instruction 1 is being decoded and instruction 2 is being fetched. In cycle 3, instruction 1 moves to the ALU, instruction 2 is being decoded, instruction 3 is being fetched. In cycle 4, instruction 1 moves to the memory, instruction 2 moves to the ALU, instruction 3 is being decoded, instruction 4 is being fetched. In cycle 5, instruction 1 is written, instruction 2 moves to memory, instruction 3 moves to the ALU, instruction 4 is being decoded, instruction 5 is now being fetched. After instruction 1 leaves the pipeline, soon after that instruction 2 will leave the pipeline and so on and so forth in rapid succession. So if all 5 stages takes 20 nanoseconds, each stage takes 4 nanoseconds. Hence, the latency for instruction 1 is 20 nanoseconds, but the throughput is 1 instruction in every 4 nanoseconds. Therefore, the speed up in throughput for pipeline is 5 times faster compared to the throughput in unpipelined manner. Therefore, pipelining improves the overall throughput of a task or process.
So what is pipeline hazards? Pipeline hazards are situations which prevents the next instruction in the instruction stream from executing properly during its designated clock cycle. This reduces the performance from the initial speedup from using pipeline processing. This means that pipeline hazards prevents pipeline processing from reaching its fullest potential to reduce time taken to execute all the processes. So the first hazard that I'm going to be talking to you about is structural hazard. It arises from resource conflicts when the hardware cannot support all possible combinations of instructions in simultaneous overlapped execution. For example, some pipeline processors may be sharing a single memory pipeline for data and instructions, and thus there may be multiple instructions trying to access one single memory simultaneously. Example in this situation, where the memory data fetch is required in fetch instruction and fetch operand instruction. As you can see for the first cycle, when it's executing its third instruction, fetch operand, which requires access to the memory, the third cycle is executing its first instruction as well, fetch instruction, where both of these instructions requires access to the memory at the same time. This will cause a conflict if there's only one memory available, as both cannot access the memory at the same time. And to solve this problem, there are two ways. The first is to add more hardware to your computer. The second way is to stall the pipeline till the resource is free. This stall is commonly known as a pipeline bubble, since it floats through the pipeline taking space but does not do anything. So the second hazard that I'm going to be sharing with you about is data hazard. Data hazard happens when an instruction depends on the result of the previous instruction. For example, in this scenario, where the second instruction depends on the result of the first instruction, the second instruction cannot start executing right after the first instruction, as the result of the first instruction has not been stored in the memory yet. Therefore, to fix this problem, the delay load approach is used, which is to insert a no operation instruction, where it will wait for the instruction which contains the data they need to store it in the memory first. Then they will start executing that instruction itself. This helps to prevent the data conflict.
In conclusion, we will be going through the pros and cons of pipelining. The pros: it has quicker time of execution of larger numbers of instructions, and secondly, more efficiently use of processor. And the cons: pipelining involves adding hardware to the chip and inability to continuously run the pipeline at full speed because of pipeline hazards, which disrupts the smooth motion execution of the pipeline. However, the pros still outweighs the cons, as pipeline hazards can be solved and prevented from happening. Thank you for watching our video.